This is the description for the assignment 1 for digital circuits course. Question 1 was asked to convert this binary number into decimal. So we know the weights, multiply the given binary number to the weights and add them up. It is done here, multiplied and summed up to generate the decimal weight. So it is a 42 in decimal. So option B is correct. In question 2, 76 in decimal base 10 was to be converted to hexadecimal. So it is simple process, keep dividing and collecting the remainders, convert it to hex numbers, and the lowest one will be your MSB, most significant bit here, and least significant bit will be here. So it is 4C in base 16 or hexadecimal. Option D is correct answer. Question 3 required 45 to be converted into base 2. So we want to just convert it into binary. Again, repeated division, collect the remainders, and this will be MSG. Write it down in correct order. MSB first, LSB is the least significant, and powers increases towards left. So bigger numbers are generated. Option C is the correct answer. In fourth question, this number is in base octal and is in base 8, needs to be converted to hexadecimal. You can simply write the binary code of these numbers, group them in 3 bits, and when you group them in 3 bits, then you can regroup them in 4 bits, and then you can write the equivalent hexadecimal number. So the correct option answer for this is option A, which is for question 4. In question 5, again binary needs to be converted, and this is the conversion in octal system. I have simply grouped them in pairs of 3. Since 2 to power 3 is 8, so octal 8 can be paired with 3 bits. 2 to power 3, this is the pairing count. So option B is the correct answer for 5. Question 6, we were asked two n-bit numbers if added. If n is 1 bit, 2 n-bit numbers is added, how much is the result? If 2 n-bit numbers are added, n equal to 2, we get this. So it is always n plus 1. This is the answer for question 6, option D. For question 7, we were asked to do something. So we have to find the sum of these two negative numbers, which should be minus 15. Since the register is of 5 bits and negative number is represented by minus, so we simply can write directly minus and 111 bit, which is option B, and we can also do the ones complement addition to get the answer. So these are the bit ranges, and you can understand pretty much the answer. In question number 8, this equation is given, unknown is x. So you simply bring this to decimal by multiplying with the base, with generating its weight, and then summing it up, which gives a decimal 30. Similarly, on the left hand side, this is the base, so we try to find the decimal equivalent. We end up with this equation, x squared plus x equal to 30. We know that if x is 5, this equation will be true, so answer is option B, 5 for question 8. Then for question 9, this needs to be converted to base 10. It is simply done using the weights on left side and right side. Notice 2 to power minus 1 goes after the decimal point. So option C is answer for question 9. In question 10, again an equation is given. This one is unknown. This time y is a number itself, not the base. So let us rearrange this equation, bring this here, this becomes minus, subtract these two numbers, you will get y. But notice it is in base 8, so in base 8 you will subtract. Note the carries will be 8. In decimal it is 10, in binary it is 2. Since this is base 8 octal, so carries will be, if this doesn't sound good, then you can do addition in subtraction in binary also, you'll get the same result. So option C is the answer for question number 10. In question 11, we need to find this number's equivalent in base 4. we simply do these two methods, we perform these two methods to get the numbers, and that is the answer. So you repeatedly multiply with the base, keep collecting the numbers before the decimal point, and these numbers go here, multiply with the base again to generate numbers until we can find, till we reach a end, or sometimes it becomes non-terminating, but it is not the case here, and this is simply conversion to another base. So the answer is option B for question 11. You can double check it also by bringing this back to decimal number with your basic method. It confirms your answer. So question 12 has answer option C. Simply get 1's complement by flipping the bits. Question number 13. 8-bit 2's complement form of minus 45 base 10. We need to write in 8-bit format. So in 8 bits we will write the number down. Then 2's complement is found by first finding 1's complement, then adding a 1 to it. So this is how we find 2's complement representation. So the answer for question 13 is option B. Further in question 14, we need to add two hexadecimal numbers. We add 2 and 0 gives 2, C and 1 gives D, C plus 1 is D, then F plus S is 15, 15 plus 15 is 30, 30 you can convert in hexadecimal, it is 1E, so E comes here, 1 carries, and so you can add it up and you'll find that option B is the correct answer for question 14. In question 15, you need to find 16-bit 2's complement representation of minus 28 in base 10. This can be done by writing this number in binary form, and answer is option C. You can see the solution. If you don't understand, you can ask me in comment section. Thank you.